Hello, everyone. Welcome to our speaker series. My apologies that we're running a little bit late. We are going to give our speaker, our own innovation engineer, Joshua Keys. He says his mom calls him Joshua. Sometimes I call him Joshua, but Josh Keys is just putting the finishing touches on a few technical glitches. It's a good thing he's an engineer. I think he is trained to solve problems. I'm going to give a little bit of an introduction. The first thing that I want to say is a huge congratulations to my colleague, Alicia Collins, who has really created this speaker series from an idea and in true Brilliant Labs fashion has just created an entire a platform for problem solvers and passionate makers to share their expertise with students from around the world and right here in Atlantic Canada. Mr. Keys, I see you've joined. All right, he's still conferring. If you're new to the Brilliant Labs meeting platform that you're joining us by, there are a few things that you may want to discover or explore. So firstly is our public chat. Many thanks to our program specialist, Kathy. She's monitoring the public chat. Should you have any questions about connectivity, troubleshooting, or really we encourage you to engage with the conversation with Josh. And so Josh will save a few moments at the end to answer some questions, but Kathy will be able to point you in the right direction should you have any comments, questions, or thoughts along the way in the public chat. We're always open for follow-up chats and conversations. If you want to email us, our email address is info@brilliantlabs.ca, or you can reach out to us on any of the social media platforms that you use. All right, Mr. Keys, if you want to give us a thumbs up, then I'll get into your formal introduction. No, I am not able to hear you. So you may want to leave the audio, come back, and make sure that Black Magic microphone is selected. So we're juggling two different studios set up here. So Josh is in our main studio behind me, and then we put together another studio for this introduction. And while oh, I see a classroom. Hello there. Hi everyone. Thank you so much for joining. So a few more notes. With the BL platform, you can do what's called focus on a speaker. And so during the speaker series, what I like to do is just where it says our name in the lower left-hand corner of the screen, you can click on that and then focus to that user. It's always really nice to see classrooms like we see Mr. Bray's right there joining us. When Mr. Keys begins his presentation, Mr. Bray and anyone else who's turning their camera on right now, I will ask you to turn those off. But then at the end of the presentation, please turn your cameras on, turn your microphones on if you would like to ask Josh some questions. We really encourage that. This is more of a conversation than a presentation. I will remind you that this session is being live streamed to a duplicate YouTube link. And so this is for memories and for us to be able to share this a little more freely beyond today's live presentation. And so if you have colleagues or other students who have missed this and you would like to engage asynchronously, please feel free to check out the YouTube version of that in the email that you registered. Hey, Josh, you look so small.
Are you able to hear me now?
We are able to hear, but don't take my word for it. Miss Smith's classroom, are you able to hear Mr. Keys?
Can you guys hear me out there?
I see a couple of thumbs up.
Okay, excellent.
Perfect. Well, thank you so much, Josh, for joining us. I know you are super busy. I have the privilege of calling you a friend and a colleague, and you are incredibly modest about your skills. Just a little bit more about our presentation today before we turn it over to Josh. The inspiration for these speaker series is to share an expertise in a really accessible way. Josh is going to be chatting a little bit, not only about creativity and robots and robotics, but by what brought him to Brilliant Labs and really dedicating an entire career surrounding helping people. I'm likely already giving too much away to his presentation. I want to remind
Spoiler alert.
Oh, sorry, what's that?
I said spoiler alerts.
Spoiler alert. Aren't I great for a few spoilers? I do want to remind everyone that you're likely connecting today on what is unceded Indigenous First Nations territory, and we're lucky enough to be able to join you today here in Fredericton on what was originally and still remains Wolastoqey lands. And so thank you so much for joining us. I see we have 15 users. Many of those are, oh no, we have more, 28 users. Many of those are full classrooms. And so without further ado, I'd like to present to you Mr. Josh Keys. He is currently the innovation engineer at Brilliant Labs. He comes to us at a point in his career where he has solved so many problems, and you've heard enough from me. I'm going to turn it over to my friend, my colleague, Mr. Keys.
Thanks, Jacob. Hi everyone. As Jacob has said, my name is Josh Keys and I'm an engineer. So I bet that when most of you hear the word engineer, right away you get these pictures in your mind of what an engineer is. Maybe I just sit at a desk all day and night and work on really hard math and complex problems trying to solve them. Or maybe I'm just someone who wears a hard hat and walks around a construction site, just pointing at different things all the time. And while some of that might be a bit true to an extent, maybe minus the hard hat part, what if I told you that engineering was actually more like a professional inventor? Let's see what Google has to say about what an engineer is. So if you Google engineer, what you see is that an engineer or engineering is the application of science and math to solve problems. And what that means is that an engineer takes really cool discoveries that scientists have made and uses them to solve problems in the world. So in essence, an engineer designs or builds or invents things to solve a problem. And I bet if you're here today that you love solving problems too. So naturally, you might ask, what does all of this have to do with robotics? Well, you probably struggle to find a robot out there that doesn't solve some sort of problem. It was designed for a purpose. But before we dive into any of that, I want to ask you a question, an important question. What is a robot? Can anyone out there unmute their mic and tell me what a robot is? Anyone? We got anyone? Okay. Maybe everyone's a little too camera shy. How about this?
Okay, Mr. Bray's students want to say something.
Okay, let's hear it. What's a robot?
What is that, kids? Machine, piece of metal. Those are some words I hear.
Machine, piece of metal. Okay, is this a robot here?
Is that a robot, kids? They're saying thumbs up. Yeah.
Thumbs up. Okay, so is it something that looks and talks like a human? It can walk around, serve us, clean our room, do whatever it is, maybe do our homework. Is that what a robot is? How about this? Is this a robot? Something with wheels that can be remote controlled from one planet to another. It can go around, it can gather samples, take pictures and videos. Is this a robot? Is this what you think a robot is? Okay, I'll ask you one more. How about a multi-articulating arm with graspers or different tools that it can use and perform a whole bunch of different functions? The kind that you'd see in a production line, maybe welding a car. Is that a robot? Well, it turns out that defining what a robot is and what it isn't is actually kind of tricky. For the case of the first robot I showed you, C-3PO, maybe you recognize from a small chain of movies called Star Wars. C-3PO was an android, or more simply, a robot that is actually meant to look and act like a human. The second one I showed you was the Perseverance rover that just landed on Mars. NASA refers to her as a she, and she is a feat of engineering. She is the most complex device ever to have landed on a planet. And she's what's called a remote controlled robot. And finally, we have the example of that manipulating arm. And if it could only rotate maybe left and right and do one thing, we'd call it a machine. But because we can reprogram that arm to do a whole pile of different tasks, thanks to that articulating arm that can move all around, kind of just like my arm, how I can move it all around in different places, we call it a robot also. Toyota Japan has a nice little question and answer website, and I liked what they had to say about what the difference was between a robot and a machine. And it says, a machine can precisely repeat predetermined motions. So it can do motions the same over and over. A robot can do that, but it can do so much more. So the machine can, or all robots are machines, but not all machines are robots. But with all of this said between the different kinds and that, why does it matter if we're talking about a machine or an android or a manipulating arm or a rover or even a cyborg? Is it important? Well, in my opinion, it doesn't matter. It's great to understand the differences right now. If you happen to be interested and want to know exactly what you specify as a robot or not a robot, or android or cyborg or humanoid or any of these things, but at this point, it's not really that important. So I'd like to ask, what does matter? At least in my opinion, again, what matters is that you can use technology, creativity, innovation to help others with your robots or machines or any device that you make, maybe even an android. And you see on the screen here, I've got a whole bunch of different blocks on here that are the United Nations SDGs, and you can see a whole bunch of different opportunities where you can help others. And it doesn't just mean helping a person in need. As you see in here, it could be helping to solve hunger, climate change, responsible consumption, or even ways to explore a new planet to help us push forward as humans, just like that Mars rover. But I also don't want you to think that doing projects just for fun is a bad thing. Sometimes our greatest discoveries can be serendipitous or just sort of by chance when we weren't even looking for it. So I've done sessions with classes on making robots out of cardboard. I've got a little video here that I wanted to show you if we can get it to play right. Oh, let's see here if I can. I don't think it's gonna let me skip forward to it. Oops. So we'll just skip that for now, but it's okay. But with cardboard robotics, we've taken a robot that we've made, a remote controlled robot, and are able to move it around and do lots of different things with it. It didn't really solve any problems, but it was actually something that gave students a chance to just learn through having lots of fun and great learning opportunities. So all of these different things that we learn can be applied to future projects that we do. Okay, let's see, I'm getting stuck on this video here. See if we can switch. There we go. So before I did all of this, I worked as a rehabilitation engineer, and that's a bit of a mouthful, but what it means is that I invented devices to help people who had disabilities to try and live as normal of a life as everyone else does. And I'd love to take a few minutes to talk about some of them in hopes that I can inspire you and your creativity in your robots, in your machines, projects, or whatever you make. So I wanted to start with one of the earliest projects that I did. I met so many incredible people, individuals that I got to work with over the years at Stan Cassidy, patients that I got to see. And I have to say that this project or even this person was really one of my favorites, if I'm allowed to have favorites. He was in a wheelchair and he had a full-time attendant, meaning there was someone who was always with him at all times. And he lacked the ability to move anything at all except for his right thumb, an index finger, and on the left side, his middle finger on his left hand. And I get confused because his arms are actually crossed across his lap. And with this, I wanted to build something. Oh, probably going to be confusing with me having two of me, but maybe to make myself a bit bigger. He had his right arm on one side, left arm on the other side, and someone actually had to place his arms in that exact position. And after a certain amount of time, he would ask them to kind of move his arms around a bit, because you can imagine if you had to sit in this exact position in a chair, if you imagine that I'm sitting, it would get tiring after a while to keep sitting in that same position. You get sore. So constantly you would get repositioned into different places. So it made it hard for him to be able to use his computer. He wasn't able to grab a mouse, move it around. He wasn't able to have maybe a mouse put in a certain spot that he could maybe move that one finger that he can move just a tiny, tiny bit. And we're talking little tiny, tiny movements. Wasn't able to do those sorts of things. So what he was able to do, at least no matter where his arms were positioned, if they were a little bit like this or like that or stretched out or in, he was still able to move that thumb, finger, and middle finger a bit. So what I looked at doing for him was making one of these first devices, which was known as the Geppetto. So if you know Pinocchio, the idea was moving fingers to control. So the Geppetto was made up of a few different devices. There was what looks like a USB drive, if any of you have used that before. Well, it was sort of like a little USB stick that would sit on his hand. It was very small. It was very light. It was on the order of maybe less than 50 grams or so. I can't quite remember. And it had little cables that went out to these things on the right side, which were these little tiny circuit boards. They were so small, they just fit on the fingernail. And there was just a little flexible thin cable that went between them. And with this, it would wirelessly take the movements on the fingertip and transmit them to this little thing in the middle called the base station, which would be connected to a computer and would act as his mouse. And with that, he was able to fully control the computer and give him back his independence so he could continue on in his job. He had a full-time job, and allow him to control. So no matter how he was positioned, every time he was repositioned, the attendant would press a reset button or a calibrate button on here to let it sort of recalibrate the position that his finger's now in. And now when he moves those little tiny movements, it's going to pick those up and allow him to move the mouse left, right, up, down, and do lots of clicking. So before I talk about the next project, I want to explain a concept to you in sort of this whole world of rehabilitation engineering or assistive technology known as switch adapting, because it's going to be important to what we talk about next. I want you to imagine that we can see inside of a mouse. So not the furry kind with the bones and the guts all inside. I'm talking about a computer mouse that you can press, you can move around. If you could see inside, well, the switch on the left side, that left click button, inside, it's just a simple switch so that when you press, the circuit closes and the mouse knows that you meant to left click. So it tells the computer, hey, Josh just pressed the left mouse on there because he closed that switch and it's going to click on whatever I actually have on there. And if we let go of it, it opens back up and it's no longer pressed. So the computer knows that I'm not pressing it anymore. Well, as you can imagine, for some people, like one of the patient I was just talking about, well, pressing buttons like this on a mouse or maybe a remote control or a toy or any device, it's not possible for them. So what we do to this mouse, to toy, to whatever it is we do something called switch adapting it. And that is we adapt the toy so that it's a little more easy to use and that a switch can be connected to it. We make it more accessible so that we can plug a switch into it. So if you imagine that we open it up, so we open this mouse up and we find out where that switch is, and we just solder wires on either side of it. If any of you have soldered before, it's kind of like welding, but on a smaller scale. You get something really hot and some metal, and we can connect a wire onto another wire by soldering. And so if we soldered wires on either side of this switch, because remember, a switch is nothing more than just actually touching those two wires together or shorting it out. And we brought those wires outside of the mouse. So now we've got two wires that are just dangling like what I've got on here. Then we put an easier switch on the outside of the device. So we've got something like this button. Maybe we'll imagine this is a big button on here that our patient can now press. So they can press this switch. Well, what we've done is we've made it so that as they press this button, that mouse or toy or remote or whatever it is will think that they actually push the button that was on the mouse or the toy or whatever it is. And those who switch adapt devices, or I should say that this is what we call a switch adapted device. So if we did this to this mouse, it would be switch adapted. And those people who switch adapt devices like to do one thing that makes it easy to connect any type of external switch that you want. So maybe someone that you were helping couldn't use a switch like this and they needed to use a completely different type of switch. Well, to make it easier, we like to replace those wires that come out with an external, with a wire that is a headphone jack. So if any of you have seen your headphones where they plug into that little sort of plug, well, you use a headphone jack with this and you say, well, why a headphone jack? Well, it could have been anything, but headphone jacks are cheap and common. So since we adapt our toys and devices with headphone jacks, since we have these adapted, and I've got something right here that's someone just passed to me. This here is a switch adapted toy, and it's kind of the guts have been brought outside of it, but on here we can see that we've got some headphone jacks that are on here all around it. So it could be brought out as a cable like that, or it could be put onto this nice little thing, which we had some students here at George Street Middle School do. But all these different buttons that were on here, they needed to solder on either side of the switch so that instead of having to press on here, we could plug a switch into here. Go back. So with this headphone jack, if we adapt our toys and put this headphone jack on there, well, it turns out that people who make switches for these sorts of cases know that they're going to have a headphone jack on it. So they make buttons that will plug in just like your headphones. So the switch you see on the screen is known as a buddy button, and is a really large switch that makes it easy to press. And in fact, there are many different kinds of switches to choose from. There's big ones, small ones, easy to press ones, ones that you can hit really hard. There are joysticks. There are ones that you can breathe into. There are some that you only have to get near to them, a whole bunch of different kinds. But the common thing about them is that they all can plug into this headphone jack. So if you're ever interested in doing something about switch adapting, or even helping someone in that case, you can contact Neil Squires, and they've got programs where you at your school can help switch adapt devices like that teddy bear to go to someone, some kid or someone else, maybe your age or younger, who wants to have a toy, but they can't actually press those buttons that are on there. So many of the people that I helped used the same type of switches that I showed on there to interact with. But there's one problem with using a switch to control something. What if you could only use one switch, but the thing you wanted to control had a lot of buttons? So if I wanted to control all the different sounds and things that this could do, but I didn't have the ability to plug in the 4 different switches that are needed on here. Well, that's why there were devices that I made, like the ones that we have on here. The one on the left was called the Stanscan Revolution, and it let you connect up to 3 switches. You could use 1 to control it, or 2, or 3, and those switches would control that sort of clock arm that you see in the middle, and it would move around. So there's a pile of different ways you could use it, but what was nice is you could have different size clock faces on there, and you could write whatever it was that you wanted to control with it. And the outputs, which were those switch jacks that you see on the left side, you could plug those into the toy. So we could plug 4 wires from there into that toy, and they could use 1 button to make the clock move around and have it actually control that toy. So they could maybe say 1 is to make it sing, 2, they could write where it says I'm hungry, it could say, make it dance if that's what it did, etc. And we had the Revolution, so this clock sort of version, but then also on the right side, there was one that just used numbers instead of the clock. And you'd say, well, why the clock? Well, for some people, even trying to think of a number was really hard for them. So some people needed an arrow to point at a picture so that they could understand what it was going to do. So someone could tape a picture onto there and actually maybe put some musical notes so that they would know that when they pressed it, they could see that arrow going on there. And we would tape different things, maybe a fun picture onto the end of that clock and have them move around and actually light things up. So this device here, there were a couple different ones that essentially allowed people to be able to use 1, 2, 3 switches, or even 4 on the one on the right to control a whole pile of different things. And that was really important. But sometimes the switches had to be really small and placed exactly in the right spot on someone's finger. So how could I do that? Well, I'd scan their finger and then design something that would custom fit on there. So something that was 3D scanned, and then if any of you have done 3D printing before, I got to do a lot of 3D printing where I could take scans that I had done or even just designs from scratch and make different things. So on the top left picture, I have someone who was missing part of their arm, and they needed special holders for their fork and their knife and their spoon. And they had someone, an occupational therapist, sort of mold a special holder for them. But the problem was it took so long to get it so perfect. They were worried, how am I ever going to get it made again if this occupational therapist can't do it? So I could scan it, I could 3D print it, and then I could even do cool things like integrating holders for forks and knives and lots of neat things. And then you see some switches. There's one right here, my head is over top of, and that was based off of someone's finger that was scanned to get sort of the type of finger shapes, and that where it could be placed on their finger in an exact spot so that they could just press in the exact spot to get that to work. So lots of different cool opportunities to do scanning and 3D printing and sort of incorporate it all with the electronics that are on there. So many opportunities for creativity, and you see a PlayStation controller on there. Again, for someone who could only operate from the top side of the controller and couldn't get some of those buttons that were underneath. But sometimes the switches had to do things like detect really small pressure changes of head movement. So imagine if you're laying on your bed and you've got your head on a pillow, and perhaps you can't really do much except for rock your head back and forth just a tiny little bit. So in this case, this switch device here used a little bag and could put them underneath the pillow such that it couldn't even feel it, but just those little differences in pressure. So if you get a bag or maybe a balloon and you just give a little squeeze on it, there's pressure changes that are happening. And if we measure the pressure changes, we can do the same thing and connect it to devices and toys and anything else to be able to control it. Now, we've talked about a bunch of small finger movements with accelerometers, big switches like the buddy button, pressure switches for your head. And even though I didn't mention it, I've made lots of devices that you can detect touch on only a small amount of movement. on little, what were sort of acorn nuts, and not the kind that squirrels eat, but the kind you can get at a hardware store. So a little piece of metal where you'd only have to touch it just a tiny little bit, kind of like those finger accelerometers. But let me ask you something. What if you had no movement at all? You couldn't move any part of your body. What would you do to control something? So let me put on a science hat here for a minute and talk about a bit of science. And I'm going to make it as easy and quick as possible. So if we've got some younger classes or those who don't understand, don't worry, we'll make sure it's nice and easy. So maybe you've learned this before in science, maybe you haven't, but if you've ever played with a magnet, you know that equal and opposites, they love to get as close to each other as possible. So think of when you have a magnet, if you put the north side and the south side together, they snap together. Well, as you start to pull them apart, you can feel that they still want to come back together. There's a force pulling on them. Well, when we're talking about sort of a single charge, as we pull them apart, so this isn't exactly the same as a magnet, but this idea of a force that exists, as we start pulling them apart, we start getting here, we start getting a force across them, and we get what is called an electric field. So we get sort of this charge between the two of them, and what we call this is a dipole. Don't worry, you don't have to remember the name about it. What I'm going to tell you, what's cool about it is that the eye, so my eye, your eye, is like a dipole. And why? Well, the front of your eye, the cornea, has a positive charge, and the back of your eye, the retina, has a negative charge. And because of this, there are forces all around the eye that we can measure. And I mean, to me, this is the coolest thing ever. So why does it matter that there's this charge all over? Well, here's where it gets even cooler. As you move your eyes, those fields move with them. So keep a close eye on the positive and the negative charges here as I kind of move through. So watch, as we move the eye, see how they're moving? We move left and right. Those charges are also moving back and forth. That's important. So if we connect some electrodes across the eye and we do a whole bunch of different circuits in that, we can sort of amplify this and make those tiny little signals actually be read. So we can see the voltage over time as those eyes move back and forth changing, because one's more positive than the other. And this is really important. So because we can do this, like, what can we do with it? Well, sometimes there's people with a terrible disease that maybe some of you have heard of, known as ALS. And ALS, or Lou Gehrig's disease, amyotrophic lateral sclerosis, is really terrible. And one thing that happens is over time, sometimes the only thing left that they can move is their eyes. So with that, missing a thing here. I made a device that measures those eye movements and put electrodes around the eye. So you can see on here that there's electrodes around one side of this person's eye and the other side, and then a third one. And unfortunately, I can't, any pictures and that of when I used it, well, they're not around because we can't really take pictures of this happening. But this is called EOG, or electrooculography. And some of you may have heard of ECG or EKG, where you measure your heart, and that's another graphy, electromyography, a bunch of different ones. So with this, we were able to measure those eye movements, and with it, be able to control different things that a patient might have connected to. So just going back to that switch adapting example, you can see on this up here, there's an R and an L on there. So if they did a quick look to the right and back, excuse me, they would be able to control something plugged into there. And if they did a quick look to the left and back, they could control something plugged into there. And that makes a world of difference for someone who has no other control. It gives them the ability to speak again, maybe through some sort of text to speech or many other different things, or get control of the computer. So many different ways that you can use this. And we don't have time today, but I wanted to quickly just mention, because I thought it was super cool, that I did a master's in engineering kind of on this whole idea. And unfortunately, I don't have time to talk about it, but I looked at ways that you could, all over the face, where you could connect electrodes and get all these signals and do really awesome things to try and make lives better for any of these patients and any of these people. But I want to pose a question for you. Why would I stop doing this stuff that I got to do to help others and sort of leave that and then come to here? And the answer to that question is because I want to teach and inspire. I want to help students like you learn to build toys or games or robots to help people or solve problems. And because you came here to talk about robots, the next question is, how can I build a robot? Well, for those of you that don't know Brilliant Labs, we love to teach through hands-on learning. We want you to learn through making, to learn through your successes and your failures. And one way we can do this is by providing you with something that can support you from the most simple of projects, electronic projects, right through to the most complex. So we designed something we call the Brilliant Labs B-board. Some of you may have seen this before. But before we talk about the B-board, we need to talk about another important part about it, what it was made for. Have any of you here used a BBC microbit before? Is this something that you recognize? Anyone out there, anyone in chat or someone? So we love the microbit. It's so versatile. It offers so many cool ways to make your projects just have so many options to be able to detect when things are moving, temperatures, so many different things. But we wanted to make the microbit do so much more. So we made a superhero cape for it. And that is the B-board. And when you put them together, you get awesomeness. When you put a microbit inside the B-board, we have the ability to offer so much more. We add spots on there to connect motors to, speakers to play sounds, microphones to hear noises, LEDs that play different or show different colors on there that we call blixels, and even Wi-Fi, way to connect to the internet so you can make smart plugs or smart lights or anything like that. And on top of that, it also supports what we call micro clipboards. And these little drop-in boards keep growing more and more. And what they are little boards that allow you to use the latest and greatest technology that's out there. And we aim to make it as simple as possible, where you can just take a clipboard and plug it into those slots that are on the top. So that one, oops, on this side right here, those little spots there, these clipboards just plug into there. And then you can just use simple blocks to be able to do this. And that's the beauty of it. You don't even have to know how to code in order to get started. For example, if you wanted to turn a motor that you had connected to the B-board on at half speed and maybe have it on for 1 second whenever you pressed A on the microbit, sounds like a lot, but this is all you need to do. You just take a simple block, and when A is pressed, turn that motor on to half its speed, 50%, for 1 second. And that's about it. This is coding. These blocks are coding. So you didn't know how you were coding before? You're coding now by just grabbing a simple block, almost like Lego, and putting it together. So another example would be a board hears a loud sound. If you wanted to maybe post the value of the light level in your room to our Brilliant Labs cloud, so put it up on the internet, you could do something as simple as this. When you hear a loud sound, I want you to put the light level up to our Brilliant Labs cloud. And that's something for another day that we can talk about. But the point is that anyone can get started right away. And we want to help you. I want to help you. So how can you get involved in making your own robot? Well, I'd like to announce two innovation challenges that we're launching here at Brilliant Labs related to robots, to give you all a chance to get your hands on and into making. So could I get our brilliant lab's brilliant Natasha Voiture to unmute her mic and announce this first one?
Yes, for sure. So our first big robotics will be Robots Got Brilliance. And this one is a fun challenge that we can also link to different UN SDGs. And there's a lot of information on our website already for it. And it's really, if you could have a robot that did anything in the world, what would you have it do? So it's really a talent show of robotics. So a fun robot competition. Yeah, that is available already. And I think my colleague Josh will be sharing the link tomorrow.
Yeah, we'll send a follow-up email and make sure that we send this information out to you. The second one, whoops, we went back. The second one is an initiative of myself and our creative specialist, Mary Weber, where we want you to send a rover to Mars. So we want you to send your rover to Mars and complete brilliant missions. So your rover must survive its launch into space, which is you mailing your robot to us, and land safely on Mars, which is when it lands right here where I am now, by May 21st, although this date may change. And with both of these challenges, if you register for them, and you can see we've got a website here, and we'll send follow-up emails tomorrow for any of you who are involved in this today. But we're gonna send out everything you need. So as part of the forms, you'll fill out, if you're just a student or an individual or someone watching, you wanna take part, we can send you a kit with B-boards, with everything else you need to compete in these challenges. And if you're a class, we can send out a few kits, just depending on your class sizes, and you can work on it as a class together. But we remember that we're here to help you. I plan on meeting with any of the classes or students or anyone to help them through some of these. We'll set up weekly maybe get-togethers or different things, and we'll send out all this information over time. But these are really exciting, and that's it, everyone. I hope you're inspired to go and create not only robots, but anything that can solve a problem and even help others or your community. It doesn't have to just be one individual person. And I hope you're as excited as we are about these two challenges that we've just launched and are ready to take part in this. So that's it, everyone. Thank you for listening.
Oh, Josh, it was an absolute pleasure to listen to your dedication to solving problems, to making everyone's life better, and to know that you've just potentially inspired dozens and hundreds of students out there to do the same. It's incredible, and we're very lucky to have you with us as our innovation engineer. So thank you.
Thanks, Jacob.
I have so many questions about creativity and robotics, but we're running out of time, and so I want to turn it over to all of you. Please feel free to turn your microphones on, to turn your video cameras on if you feel comfortable doing that, or just in the public chat. While we have Josh here, do you have any questions about what he presented, robotics in general, solving problems? Now's your opportunity.
Yeah, I know it's a lot of stuff that I talked about, and sort of the point of this whole thing is just to inspire you, to get you to think about not only just robots, but just ways that you can use technology to learn, to help, to create, to innovate, to do all of these different things. This is what's so important to us. And we hope that you as a teacher or students feel inspired. And we think that these challenges are a great way to get involved and to get started, especially with robotics, with this idea. And for those who are looking for more hands-on sort of with robots, that's something that we'll get into. So if you join the challenge, we'll certainly be supporting you and helping your class in that to actually make robots and get into sort of more the nitty-gritty, the hands-on that we can do, as it's kind of hard to do without you actually having this stuff.
Josh, I see a few people who are composing a question maybe, or simply a message of thanks in the window. For those classrooms who do have to leave at a 2:15 hard stop, we want to thank you very much for joining. All of this has been recorded, and so you can access the link later. But if you do have questions, we can, Josh, do you have a few moments to stick around later?
Absolutely.
right now? All right, so I'm just gonna look and yeah, are there age groups for the Mars mission?
We are going to base it on who we have. So if you want to submit or register for it, and we'll certainly adapt based on who actually submits stuff or who registers for it. So we haven't put together exact ranges of if the missions will change for the competition, but we have it available so that any grade can register for this, and we'll do our best to support your students to get through this. So we encourage any one of you to register for this.
Yeah, at Brilliant Labs, we really encourage students, as you just said, Josh, of all ages, to really consider what a mission to Mars or a robot completing a talent. You know, what would it be? And we very much live in this world of what are these crazy ideas and how close? I mean, going to Mars is a crazy idea. Building a robot of any kind is a crazy idea. How close to pulling that off can we get, and what will we learn along the journey to get there? I'm just looking to make sure that we don't have any other questions. You know, my question, and Josh, where we geek out about this quite a bit, is this idea of really it's an illusion that robots have this humanoid. I love the fact that you have this picture of C-3PO, but I didn't know how elusive of a term robot really is. And maybe with your help of defining that, we may move away from associating a robot with a humanoid. You know, I remember the Jetsons, and oh my goodness, I'm forgetting the name right now of the helper robot there. But there are a lot of humanoid robots. There are a lot of robots that look like cars. So maybe your help of a definition will expand that a little bit more.
Yeah, we want to expand it and then just help the students not to focus on whether it's a robot or not, but just to try and innovate and create, whether it's a machine or a device or anything else like that.
Awesome. Well, listen, we will end it here. Thank you to everyone who's joined. Josh, thank you so much for being a part of the team, for presenting today, and really adding on to the shared brilliance that is the Making a Difference speaker series. It's encouraging to see the difference that you made in so many of your patients and the forthcoming students that we have an opportunity to work with. So thank you so much for sharing. Many thanks to Alicia, who's still on here and joining and is the creator of this brilliant speaker series. Please stay tuned for our next speaker series coming up on April, oh my goodness, 11th. I think I may be getting that wrong, but it's yet another great example of how people are using and harnessing their own brilliance, the 15th. Thank you. And so there are a few more speaker series that please check out our social medias to stay in touch.
Excellent. Thanks, Jacob. Thanks, everyone.
All right, I'm going to end the recording.